Namaste. Okay, all right. I wanted to do a follow-up video that you're going to need because I know I made the other one like 20 minutes long, but I don't see any way getting around it. Just kind of got to get this information out to you guys. So make sure you're taking notes. Make sure you're paying attention. Okay, so I want to do a follow-up on the spring situation. So let's say we have the situation again where we're going to do some analysis. So today I'm going to use my colored chalk, which I love. I got this at the hardware store. All right, this colored chalk. You see that? I got that at the hardware store the other day. It was like 50 cents, whatever. All right, so here we go. And so let's say here's our table, like that, and here's the wall. And then we're going to have our spring mass system again, okay? And we're going to call it an oscillator, all right? Even though that's green, I can see on the camera it doesn't really look all that green. But whatever, let's just go with it. So here's our equilibrium position, x naught, which is 0, all right? And we're going to put our spring on it. And then we're going to have our mass on the spring. And I think you can see it. Yeah, you can see it. All right. And the spring is going to oscillate back and forth, okay, like that. And let's say that it oscillates at a maximum distance. I'm going to stretch that out there. And that's going to be our amplitude A, so that the mass will come out to here and will go to an equal distance on the other side and then back and forth and so on and so forth. Okay, so in the other video, I talked about the energy or the potential energy stored in this system, and that the energy is 1/2 kx squared, okay, and that comes from the graph of force of a spring versus how much you stretch it, and k is the spring constant. All right, so let's look at that. And at the center point right there, okay, let's say we wanted to know how fast it's going. At the center point, just like with potential energy, all right, and kinetic energy or gravitational potential. This is potential energy up here. It's all potential before you let go. Then when you let go, sorry, all right, when you let it go, it changes to kinetic, and then at the point of impact, at the 0 point, it's all kinetic energy. All the potential up here is now all kinetic at the 0 point. So if I were to compress this spring, or actually let's say it's stretched out here, it's all potential again, okay? And then it goes back and all that potential energy changes to kinetic energy as it hits that 0 point in its oscillation. So at that point right there, all of this is kinetic energy. It's 1/2 mv squared. Let's say I want to solve for v. How fast is it going at that point? Pretty easy. If I know, let's say I know the spring constant and I know the distance I stretched it back, I'm going to switch that to A, the amplitude, okay, which is the maximum distance that's stretched back. The 1/2 goes, and I can say that v squared is equal to k a squared divided by m. All right, and then what I'm going to do is I'm going to take the square root of both sides, and that's going to put a big square root sign right there and just turn that into a v. Let's take a look at this for a bit, all right? And we're going to do some unit analysis on this. The a, if it's squared, then the square root of a squared is just a. So I'm going to pull that out, okay? And then I have square root of k divided by m. And now the units on velocity have to be meters per second. That's a speed. So that means these units right here have to be meters per second. Well, you can see where we're going with that. All right, A has units of meters, but what do the units of this term happen to be? Well, let's take a look at that. Okay, so I want to look at that. I'm going to erase up here. All right, save my board space. And let's do unit analysis on A square root of k over m. Okay? And let's see what the units are on this. Well, A is meters, but let's look at this term right here. So we have the square root of k is newtons per meter. That's the units on now be careful, don't get the m screwed up. Over here, m is mass, the mass that was on the spring. Here it's meters. This is unit analysis, okay? Newtons per meter are the units on spring constant, and then I have the units on mass, which are kilograms. Okay, well, let's expand this a little bit, because the units on newtons, 1 newton is 1 kilogram meter per second squared. Where does that come from? Comes from Newton's second law, F equals ma. Kilograms, A is meters over second squared. So let me expand that. So I'm going to have meters on the outside here. Big square root sign. Okay, instead of newtons, I'm going to write kilogram, okay, meters over seconds squared divided by meters and kilograms. So you can see the kilograms are going to go right away, all right, and that leaves me with big square root meters per second squared divided by meters. Okay, the meters go, and that leaves me with, all right, in that term, so I have big square root. Okay, let's just look at this term right here. All right, that leaves me with units of 1 over second squared under the square root, all right, which is just 1 over seconds, okay, which is good because that goes with the meters over here, and I'd have meters divided by 1 over seconds, and that just gives me units. And let me put the m in there, sorry, I should have done that. M, meters, and then I have meters times 1 over second, which is the same thing as meters per second. Okay, I want to look at this term right here though, okay, which we got from up here, K over M. So let me erase this and let me tell you what this means. Okay, this term is square root of K over M. Again, for you future engineers and you AP students, pay attention to this, all right? This has units. This winds up having units of 1 over seconds, okay? So what? Well, 1 over seconds is a unit of something called frequency. Frequency, there'll be another lecture on this, right? Frequency is the amount of time or the amount of cycles completed in a given second. So if you have a system that repeats itself, a pendulum that goes back and forth, it's the amount of times that the pendulum goes back and forth in a second. It's the amount of time, in the case of the mass in the spring, that the mass in the spring vibrates back and forth, goes through one complete cycle, from start out to finish in 1 second, okay? So this is units of what's called frequency, and 1 over seconds is defined, instead of saying 1 over seconds, we have a unit for that. It's called 1 hertz. Okay, after Heinrich Hertz, physicists who study this stuff. Okay, and so a hertz is a vibration or a cycle per. A hertz is a vibration or a cycle per second. All right, is what that stands for. All right. Anyway, so what that means is if you have, for example, 3 hertz. Okay, that means that the device, the pendulum or whatever, is going back and forth 3 full times every single second. Okay, you might have seen this on, if you still use a car radio. I don't, because I always use my phone to listen to music in the car. But if you're using the radio, okay, like that, so for example, the radio station 92.3 FM is 92.3 MHz. All right, megahertz, M stands for mega or million, which means that the radio wave going into the radio, when you're listening to that channel, when it's tuned into that channel, is vibrating up and down 92.3 million times every single second, and that's what it means, okay? All right, so that being the case, how do we interpret this? What's the big deal? What do we care? This term right here is what's known as the natural frequency. All right, of the, now listen to the term, it's the natural frequency of the oscillator. It's the frequency that if you let it go, all right, if you disturb it and let it go, it will vibrate at. Now notice it doesn't depend on amplitude at all. Okay, the natural frequency, so just like if you have a pendulum, and we did this, okay, with pendulums. So here's a pendulum. A pendulum, here's the, when it swings, here's the 0 point right there, the lowest point. It doesn't make a difference if you release the pendulum from up here or down here. The amount of times it will go back and forth in a second is the same. Okay, and that's something that you guys found out earlier on in the year when you did this with pendulums. All right. And anyway, so there's that. So this is the natural frequency, all right, of an object, which is and it's sometimes also called the resonant frequency. Okay, so if you ever, all objects, I should say, have a resonant frequency that if you disturb them, they will vibrate at, including you. Okay, now if you've ever seen, like if you've ever taken a glass, and do this while your parents aren't looking, take a wine glass. Okay, don't put wine in it, just leave it alone, just ting it like that. And when you do that, it's going to ring. That ringing that you hear is that sound is the natural frequency of the wine glass, or the resonant frequency of the wine glass. When you play an instrument, okay, if you pluck a string on a guitar, it makes a noise. The string vibrates back and forth at its natural frequency. In fact, all instruments, musical instruments, they're devices that human beings have invented that you can change the natural frequency of very quickly, so you can make music. So when you pluck a guitar string, it vibrates at one frequency. If you put your finger on the string, up at the neck of the guitar, all right, and you choke it down there, it's shorter, all right, and then you pluck it, it will have a different natural frequency. Okay, so anyway, just want to give you guys that concept because you're going to need it to do the problems that I'm about to assign to you. So good luck, Godspeed, keep a crowbar close to you, and enjoy your apocalypse. I know, I sure am.